was not good. Right, so I'm now turning on the recording. So anyway, get back to where I was. All right, so for people who's listening to the recording, starting to do a review of chapter 8. All right, this is of course the bell-shaped curve for a population with a mean of 8.3, standard deviation 0.8. This is a population information here. Now, if we were going to draw the sampling distribution curve, well, we would have to have a certain number of samples. For example, we could have 500 samples, and we could have 50 samples, 1,000 samples, a million samples. They all would all, now if we're looking at a sampling distribution, let's say we have 500 samples, they would all have the same sample size. So for example, sample size 5, that means all 500 samples would have sample size 5. That would be A here, this histogram here. Or we could have 500 samples of samples, each one having a sample size of 10, or 20, or 30. So now let's see a little better. Notice that as the sample size increases, the sampling distribution's standard deviation or spread tends to be more narrow. That's a good thing. You will always want the standard deviation to be as small as possible. And that one way of doing that is increase the sample size. Now, what we're looking at here are 500 samples each. Okay, 500 samples each. Okay, but different sample sizes for each of those 500 samples. So these histograms refer to the sampling distribution of 500 samples. Each one of these has, for each of the samples, has a different sample size. Is that really clear the way I'm talking here? Each of these 4 histograms have 500, refer to 500 samples, each one. Each of those 500 samples has a particular sample size. 5 for this one, 10 for this one, 20 for this one, 30 for this one. And the whole point of this little exercise here is to show you that the sampling distribution becomes, the standard deviation of sampling distribution becomes more narrow as the sample size increases. This is something that you will see later. The question I like asking on tests and final exams is this particular idea. That as you increase the sample size, the standard deviation of the sampling distribution becomes smaller. And you'll be able to see it through formulas also. But this is one way of looking at it visually. Right, so make sure you take notes on this, all right? Now, if the population distribution is, now in this particular case here, this previous case here, the population from which those samples were taken is normal, bell-shaped. And as you can see, no matter what the sample size, this is in another thing, no matter how big the sample size, any sample size will do. Notice all 4 of these look normal. The sampling distribution will be normal regardless of the sample size when the population is normal. That's something you should know. It's an important fact for this test and for the final exam. I'm bringing it up. All right. Now here's a case where the population distribution is not normal. It is skewed to the right. All right, pretty obviously skewed to the right. Suppose we took 500 samples of different sample sizes, starting again with 5, 10, 20, and 30. Notice that for 500 samples of size 5, sample size of 5, and the population is skewed right, notice that this doesn't look that normal. It looks somewhat normal, but not normal. It still looks skewed to the right, not as bad as the population. Notice that as we increase the sample size to 10, again, the spread is becoming more narrow, but let's just look at the shape. The shape is starting to look more normal, but it's still skewed slightly to the right. Notice it becomes more normal as we get to 20 for the sample size for each of the 500 samples, but it certainly looks normal when we get to 30. And actually, as we'll find out, 30 seems to be that magic number. When the sample size is 30, even if the original population is skewed, the sampling distribution, we can say, is approximately normal. All right, and that seems to be the minimum sample size. Now, it does vary from different fields of different subjects like sociology, psychology, chemistry. Regardless of what your research is on, there's going to be some variation of what a minimum sample size should be when the original population is not normal. But in general, we say 30, all right? And that's what you should know. 30 is that minimum value. So here in review, if the original population is normal, then the sampling distribution should be normal for any sample size. If the original population is not normal or unknown, right, then the sampling distribution becomes approximately normal when the sample size is at least 30. Now, this is true. I should make this really clear. This is true, what we're seeing here, for cases where we're looking at the sampling distribution of sample means. There's a special case when we talk about the sampling distribution of proportions, which I'll talk about it in a little bit. All right, but just know that the this n is equal to 30 is just for the sampling distribution of sample means. We don't use that for proportions. You should make sure you know that. All right, that's going to be important for what's coming up this week. All right, in terms of tests and things like that. Any questions about that? I hope you are paying attention. Now, what's the general properties of the sampling distribution of X bar of sample means? All right, so some of the symbols that you need to know for this, again, is X bar is the sample mean, N is the sample size, mu is the population mean, sigma is the population standard deviation. Mu with a subscript of X bar is the mean of the sampling distribution of sample means. All right? It's the mean of that sampling distribution of sample means. And sigma X bar is the standard deviation of the sampling distribution of sample means. And here's the property that you should know. Regardless of the sample size, it doesn't matter what the sample size is, the mean of the sampling distribution is always going to be equal to the mean of the population. It doesn't matter the sample size. If I give you the sample size, you ignore it for property 1. Sample size doesn't matter, but it does matter for property 2. The standard deviation of the sampling distribution of sample means is equal to the population standard deviation divided by the square root of the sample size. The sample size does matter for the standard deviation part here. You need to know this. You need to know property 1 and property 2. And if I were you, I'd memorize it. All right? Don't just tag it and say, I'll get to this during the test. These are 2 things you should already probably have memorized. But if you haven't, memorize it. Now, they mention here that the second formula here, property number 2, is exact if the population is infinite, and it's approximate if the population is finite and the sample size is no more than 10% of the population size. All right, that's fine. That's okay to know that. But for all intents and purposes for this course, as far as calculations are concerned, we're going to assume this to be true. It's property 2. We'll just assume it to be exact, even though it's an approximation in many cases. It's a good approximation, so we'll assume it to be a fact. All right? Property 3 is that when the population distribution is normal, the sampling distribution of X bar, or the sample means, is also normal for any sample size. The property 4 is called the central limit theorem. It says that when n is sufficiently large, the sampling distribution of x bar is well approximated by the normal curve, even when the population distribution is not normal. So I'm going to rephrase property 4 by saying, if you know the population distribution is skewed or not normal, or there's no information about the shape of the population distribution, and property 4 becomes important, the central limit theorem. Now, when is n sufficiently large? When n is at least 30. Remember, these 4 properties are for the sampling distribution of x bar only. All right, only x bar. Get to proportions, it'll have its own set of properties, which we'll look at. All right. Notice now with the formula, this is why I was telling you before, as the sample size increases, the sampling distribution spread or standard deviation gets smaller. Remember I said that earlier? You can see that through the pictures. Well, here's the reason. The standard deviation of the sampling distribution is the population standard deviation, which is fixed, divided by the square root of the sample size. You know from arithmetic, when you studied it in high school and middle school, that if you have a fraction or ratio, if the numerator is fixed, if you increase the size of the denominator, the whole ratio becomes smaller. Okay? You should know that. All right? As n gets larger in this formula, sigma x bar gets smaller because the numerator is fixed. All right? That's arithmetic. All right? That's from, I think you started learning that in middle school, 8th grade, I believe, was when these types of relationships were, people were starting to look at it, because that was the time that you started algebra, right? In the 8th grade. All right. What else is that we could see here? Well, this is another picture of the idea that if the population is normal, then regardless of n, the shape is going to be normal. But as n increases, the spread becomes more narrow. Here's a population which is skewed right. Doesn't have to be skewed right, but this is an example. Notice that as n increases, it's still skewed right for small values of n, but when we get to 30 for sure, n becomes normal. Now in this case, they say 16, but just know, and this is just a bad illustration, that the first people writing this textbook should know better. They gave a bad example here, but n is 30. They should put 30 here because students would get confused thinking 16 is the minimum sample size for normality, but it's actually 30. All right. So this is just an illustration to show that as n increases, the sampling distribution becomes more normal if the population is skewed. Now here is the
normal sample size is a minimum of 30.
All right, let me rephrase that again. Let's go back to that. Let's read it. Let's read it carefully. This is properties 3 and 4. If the original population is normal, the sampling distribution is normal for any sample size. However, if you know that the population is not normal, or we don't have any information about the population, then we want n to be at least 30. All right, is that clear to whoever asked the question? All right.
Yeah.
All right, 30 is not a minimum for any situations, only in these situations here. You got to read this carefully. All right, this is like a recipe book here. It says if the population is normal, then the sampling distribution is normal, period. Doesn't matter the sample size. Property 4 says if the population distribution is not normal, then n has to be sufficiently large, and I'm telling you that's 30. Okay? Is that clear? Person asking the question?
Yes.
All right, good. Now, here's the z-score formula for samples, for sampling distributions. If we have a particular sample, Remember way back when we learned about z-scores, and we had individuals. Let's say we gave out a test, right? And somebody, you know, the mean was 100 and the standard deviation was 10. And let's suppose somebody scored 110. We know that the z-score is 1, all right? Which means that person scored 1 standard deviation bigger than the mean. This is something different here. This is the same z-score formula. It's calculated exactly the same way. We take our original value and subtract the mean and divide by the standard deviation. But in this case, notice that the value that we're putting in the numerator here is not an individual score. It's a mean of a bunch of scores. So if the sample has 100 people, X bar represents the mean of those 100 values, whatever they may be. Let's say they're test scores. So X bar refers now to not one person, but 100, the average of 100 people's scores. Because we're dealing with a sample, we must use the sampling distribution to calculate the z-score. So because it's X bar here, we have to subtract the mean of the sampling distribution and divide it by the standard deviation of the sampling distribution. Is everybody clear on that? So if it was one person's score, it would be X minus mu divided by sigma is our z-score. But if it's a mean of a sample of 100, let's say 100 scores, then it's going to be X bar minus mu X bar divided by sigma X bar. Now we're dealing with samples. Now the right side of this, we're converting that to the original population and standard deviation symbols, because we know that the mean of the sampling distribution is equal to the population mean, so we can replace mu X bar with mu. And we know that sigma X bar is equal to sigma divided by the square root of the sample size. So I hope you could see how we progressed to the right here. So this is this formula for the z-score, and this is important when we do hypothesis tests, because hypothesis tests use z statistics, they can use t statistics, but it's the same idea, that we have the numerator here, and then we have this denominator. This denominator, by the way, another name for it is the standard error. All right, so the standard deviation of the sampling distribution is also called the standard error. That you should know that. All right, and I think the rest here is just some examples. I'm not going to go through the examples. I'm going through the logic of these chapters. All right, and I think that is it for this chapter here. So I think the rest of it is, yeah. All right, so let's go to chapter 9. I want to make sure to cover the basics of chapters 8, 9, and 10. All right. Right here. Go to chapter 9. Now, 9 has to do with estimating a population mean or a population standard deviation using what's called a confidence interval. Now, this chapter comes up with an idea first of a point estimate. If we were going to estimate a population mean, naturally, one of the things that we might want to estimate it with is the the sample mean. In the same way, if we were estimating a population proportion, we may want to use one estimate, one sample mean, to estimate the population. The one sample proportion to estimate the population proportion. That's called a point estimate. So the sample mean estimating the population mean, the sample proportion estimating the population proportion, they're called point estimates. Now, what is the problem with point estimates? The problem with point estimates is that because there is sampling variability, if different members of this class took a random sample and came up with a mean, sample mean or a sample proportion, you would all probably get different answers because you would have different people or things in that sample. And therefore, your point estimates would all be different. That's again called sampling variability. So a better way of doing estimating the population mean or population proportion is to come up with an interval of values instead of a point estimate. So really, just this little one definition here in 9.1 is all we need. Okay, understand what we're talking about. And let's now go to 9.2, where they look at confidence intervals for population proportions. So this is an all right, let's go down. So a confidence interval is an interval of plausible values for a population characteristic. And we create this confidence interval by doing what? By taking our samples point estimate, and adding, subtracting from it what's called the margin of error. And that's a general formula for a confidence interval. It is the point estimate plus or minus the margin of error. Okay, and the point estimate is easy because it's either given to you in any problem or you calculate it. All right, but it's either going to be the sample mean or sample proportion. That's your point estimate. The margin of error is going to be something that we need to know about. But in addition, you need to know this other term here called confidence level. And it says this is the success rate of the method used to construct a confidence interval. Now, what's the method that we use? Well, we take our point estimate and we add and subtract to it the margin of error. So so that's our construction. That's how we're going to construct it. There are other ways of constructing a confidence interval besides that, but that's the way we're going to do it. And the confidence level says, suppose we had 1,000 people creating the same type of sample and coming up with a sample mean or sample proportion. They will all have a different point estimate, but if they all follow the same construction, calculating a margin of error and adding and subtracting it from that point estimate, if we said something about a 95% confidence interval, each of those people who did samples would all have different point estimates and would all have different confidence intervals, even using the same construction process. But we would expect about 95% of all those confidence intervals to contain the true population mean, which is what we're trying to do here. We hope when we construct a confidence interval that the true population parameter, in this case a mean or proportion, is somewhere in between those endpoints, the left endpoint and the right endpoint of the interval. We expect about 95%. If it's a 95% confidence interval, we expect about 95% of all such intervals, which all would be different, because there's all going to be different point estimates. But we expect about 95% of them to contain the true population proportion. And that means 5% don't. If it's a 95% confidence interval, we would expect 90% of all those intervals to contain the true population mean or proportion, and 10% will not. So that's the theory behind doing it. This is very important. A confidence level does not say probability. If we construct a particular confidence interval for a particular mean or proportion, that interval either contains the true population mean or proportion or it doesn't. It has nothing to do with probability, confidence level. It has to do with how confident are you that this particular interval that you have, because this is the particular sample that you got, contains the true population mean. How confident are you? Is it going to be one of those that do contain let's say it's the 95% confidence interval. Is it one of the 95% of all such intervals? Would it be one of those? Or is it going to be one of the 5% that don't contain the true population mean or proportion? All right, that's what we mean. And it's not a probability. We're not saying if I say 95% confident, it doesn't mean there's a 95% probability that the true population mean is in that interval. No, it has nothing to do with probability. All right, so that's important. Now, if we're dealing with proportions, this is the formula for the sample proportion. You should already know that. The denominator is the sample size. And the numerator is the number of people in the sample who answered the question a certain way. You know, yes to a question, or they're being asked, you know, are you going to vote for a certain political candidate? And you count the number who do. That would be the numerator. So you're just counting the number of people who answer a question a certain way and divide it by all the people that you asked the question to. All right, that's the sample proportion. That's p hat. All right. Now, the sampling distribution of p hat is centered at p. What does that mean? That means the mean, here, look what we're saying here. The mean of the sampling distribution of sample proportions is going to be equal to the population proportion, period. That's true. And number two, here's the standard deviation or standard error of the sampling distribution of sample proportions. And notice it is the square root of p times 1 minus p divided by n. Okay, that's the standard error, all right, for the sampling distribution. Or we could just say it's the standard deviation of the sampling distribution. But standard error is typically used for this formula. Now, here is the big deal. You must know this. When we dealt with the sampling distribution of sample means, remember 30, right? Remember that 30 n is equal to 30. If the population was not normal, we needed at least 30 for the sample size. This is not true here. I'm repeating this. It is not true here. It says here we have a special calculation we have to do when we're dealing with proportions. We take n and multiply it by p. We take n and multiply it by 1 minus p. Both of these numbers has to be at least 10. If they're both at least 10, the sampling distribution of p hat is considered to be approximately normal. But it must be these calculations. You cannot just say n is 30, it's normal. Not in this case. I don't know how many times I have to repeat, and I know some of you will still think it's 30. All right, but you need to write this down. This is the formula for proportions, sampling distribution of proportions. You must use this. All right, so this is the standard error formula right here, p square root formula. Now, if you are estimating with a confidence interval, the population proportion, then the only thing that you will have available to you is the sample proportion. And therefore, for confidence intervals, you'll replace the p here and the p here with p hat, the sample proportion. So when you come up with a calculation for the standard error, you must replace p and p here with p hat because that's all you have. You don't have the p because you're estimating it. All right. Now, if the confidence level is 95%, then when you draw your, and the sampling distribution is normal, then you will draw your normal curve for the sampling distribution, and you will take your normal curve and block off in the middle to 95%. So if your confidence level is 95%, the area in the middle is 95, and that means the lower tail and the upper tail are each 2.5%, because there's 5% left if the middle is 95%. And the left tail and the right tail are equal to each other because this is a symmetric curve. So this is really important. In your calculator, when you are calculating the critical value for confidence intervals, the critical value, which is going to be a z or a t, if I say 95% confidence interval, the area that you're going to use in inverse norm or inverse t must be the middle area plus the left tail area. I'll repeat this. It's the area to the left of your critical value. For example, the critical value is 1.96 here. All right. Now we don't know that if we do inverse z, or excuse me, inverse normal. But if we do inverse norm in our calculator, and we want to find this 1.96 here, we must use the area to be 0.975. If I say confidence level 95%, do not put in 0.95 as your area to the left. It is not the area to the left. It is that 0.95 plus the left tail. And the left tail in this case is 2.5%. So 95% plus 2.5 is 97.5%. Is everybody clear on that? Because I'll tell you, in your test on Wednesday, all right, some of the wrong answers are going to be ones where you forget to do that and you put in the 0.95 in for your inverse norm or your inverse t, and you think you got the right answer. No, you won't, but it will show up in the answer key. So I'm giving you a warning here. You must put in 0.975. If the middle area is 90%, if the confidence level is 90%, the middle area will be 90%. What's left? 10%, 5% on the left, 5% on the right. So what are you going to put in for your area to the left for a 90% confidence interval? You're going to put in 0.95 because it's the middle, 90 plus 5 on the left. All right? So if you weren't clear about it before today, you need to be clear about it now, because if you forget to do that, you will pick an answer thinking you got it right and you will get it wrong. Okay? And then once you have the correct critical value, now the critical value here is 1.96. Notice the critical value is being multiplied by the standard error. And that's the construction process in creating a confidence interval. And let me say this really clearly to you. The margin of error that you're adding and subtracting, see, you're adding and subtracting something to p hat here. The margin of error is always going to be a critical value, which you're going to use. You're going to find it using either inverse norm or inverse t. And you're going to multiply that critical value by the standard error. The margin of error is the critical value times the margin of error. And here's something extremely important I'm going to tell you right now. The critical value increases when the level of confidence increases. As you increase the level of confidence, the critical value goes up. And when the critical value goes up, this whole margin of error formula becomes bigger. And then when you add and subtract it, the length of the confidence interval becomes wider. On the other hand, if you increase the sample size, the standard error becomes smaller, and therefore this whole margin of error becomes smaller, and therefore the length of the confidence interval becomes more narrow. I like asking questions like that, but that's what you need to know. By just staring at the formula here, you can tell those two features. All right? Any questions about confidence intervals? And by the way, there's two ways that we can write a confidence interval. We can write it this way with parentheses and a comma in between, or what we can do is say P in the middle and then use less than this number and then greater than on the left side this number. You can do it as an inequality. You can write it both ways. All right? Just know it can be written both ways. And then finally, I want to just mention to you, we're not going to get to hypothesis tests, unfortunately, but I do want to mention something about section 9.3, the idea of the t-distribution. And here's something that you need to know. All right, we have one more minute. If you're dealing with a sampling distribution and we're trying to estimate a population mean, if the population standard deviation is unknown, then the standard error is different. All right, if this population sigma, if population standard deviation sigma is unknown, we're going to use the sample standard deviation instead, S, and the standard error becomes S divided by the square root of n. If the population standard deviation is known, okay, then we use sigma divided by the square root of n as the standard error. Now, if sigma is unknown, then the critical value becomes a t. And we're going to use inverse t to find that critical value. All right. And then they talk about degrees of freedom in here. So just read over that idea of degrees of freedom. And then finally, with hypothesis tests, this is the last thing I want to mention in chapter 10. Just know that there are 3 types of hypothesis tests. Okay. There's left tail, right tail, and two-tail. And the two-tail test, remember, when you calculate the p-value, whatever area that you're finding, you must multiply it by 2 to get the true p-value. And in the hypothesis tests, when the p-value is less than or equal to alpha, which is the level of significance, right? The probability of a type 1 error. And less than or equal to alpha, when the p-value is less than or equal to alpha, we reject the null hypothesis. When the p-value is greater than alpha, we do not reject the null hypothesis. That's the general idea. All right. And remember, the alternative hypothesis determines whether you have a left tail, right tail, or two-tail test. When the alternative hypothesis says less than, it's a left tail test. When the alternative hypothesis says greater than, it's a right tail test. And when the alternative hypothesis says not equal to, it's a two-tail test. All right. So that's all I will say about it for now. Any questions? Because we're running about a minute behind, but I think all of you should be able to finish the quiz on time. All right. Okay. So take a look, see if you see the quiz. This is the last quiz for the semester. I believe it's quiz number 6, I think, whatever it is. The last one for today should be in today's, right? Give me a thumbs up if you see it. Great. All right. And a lot of it is just to review what I went over today, plus some hypothesis test things. But of course, if you've been doing the homework and listening to my lectures, you should be fine. All right. So again, this was I just want to say thank you for being my students this semester. I don't know if I'll have a chance to say this either Wednesday or next Monday, but I appreciate everything you've done. And I know it's been difficult given COVID and everything else, but you all hung in there, and I'll assure you, you'll do just fine. So good luck with everything. Good luck in the future, and do well on the test, on the quiz today test, and also on the final exam. If you have any questions, of course, you can always email me. And if you need to set up a Zoom session, you can do that too. All right, I'll let you work on the quiz. Just one more thing to everyone. I will do a short video, which I will post in Canvas over the next couple days, showing you how to type things in for the final exam. There's part that you will be typing things into Canvas instead of multiple choice, and will be typing your answers in. So I will give you some hints about that, some tips about that in this video. I'll send you an email when I've created that video. I'll post it in Canvas.